And now I hand over to Per Andersson for the first demo.
Thank you so much. Does the microphone work? Can you actually hear me? Great, thank you. So the name of the first demo, or the title of the first demo, is RISC-V, of course, enabled low-power CNN classification in edge devices. And my name is Per Andersson, as already been said. Thank you for the introduction. At the bottom, there are a number of logos. The first one to the left, it says Classic, which is an interdisciplinary, cross-disciplinary competence center in Sweden, encompassing Lund University and one other university and a number of companies. And two of the partners from the commercial side are CodaZip and Acconeer. CodaZip are, of course, here. Someone waving? No? Yeah? Exactly. And Acconeer, their logo is on here because we're using their radar sensor. So, having said that, who are we? We are the Integrated Electronic Systems group at the Department of Electrical Information Technology at Lund University, which is sort of a mouthful. But the way we sort of think of ourselves is that we're a team of cross-disciplinary experts from applications through innovative architectures to actual silicon realization. So we try to bridge all of that in what we do. And as such, we should have had a real piece of silicon demonstrating what it's we do here. We actually have it in the lab. It's being brought up right now. So we did what we're going to show you in real silicon. So there is a 22 nanometer die back, and we are going to bring it up hopefully already next week. We'll see. So today we're going to show the functionality of this. The actual power measurements and so forth will have to wait a couple of weeks. So the application that we're going to show you today is quite simple-minded in a way. It's a radar sensor, and it's a very low-power radar. So it's by our friends from Acconeer, and it's a pulse-coherent radar. It extends like that long from the radar sensor, and it's useful for this type of application, gesture detection. And the way Acconeer recommends that you implement that kind of a function is through a neural network. So they provide the basic software, the basic readout from the sensor as a stream of data, and on top of that you train a neural network. And for this application, there's basically 3 classifications. No one is waving. There is a hand stable across the sensor. Note that the sensor here is in a cardboard box, just to prove that this is actually a radar. So it looks through materials like that. And you can wave. Well, he is Sergio. He is doing the demo, so I should just stay away from the physical stuff. So anyway, those are the 3 classifications that we're looking for. Actually, in this application, there are actually dual neural networks, and I'm coming back to the explanation for that a little bit later. So what we do has a number of ingredients. There is the sensor, there is machine learning, there is a RISC-V, there is a near-memory computing coprocessor. And just to go a little bit outside of this particular application, the way we solve this is completely scalable. So we can go to basically any number of neural networks. It's concurrent processing. It's done with on-chip memory. It's designed to be flexible, but it's optimized for CNNs. And the main focus is power reduction, not increasing speed. This is edge stuff. It's going to sit in a low-power environment. So for the system diagram showing what we actually put on that piece of silicon that I showed you on the first slide, looks a bit like this. Then, well, this is also all the stuff related to this actual application. So there is a radar sensor to the far left, down left, and there is this microcontroller. It's a special story about having an extra microcontroller there. I'll tell that a bit in a few seconds. And then there is whatever is on the actual physical chip, and right now it's on an FPGA to be demoed here. And our sort of pride in this is that there is a programmable near-memory computing coprocessor here. It's a mouthful. What it means is that we can do neural network inference in this engine with very little data movement. And the main gain of that is that we can reduce power. So the demo is a real-time FPGA twin, if you will, of the actual physical device. And we can demonstrate the CPU offload. And basically, what we are selling to you today, or selling is perhaps the wrong word, but we're showing you that we can reduce the load on the CPU by 98% by adding this type of hardware to the side. And that translates into a great power saving. I don't have a number today because I don't have the measurements from the chip. So we're keeping you in the dark of the exact numbers, and we hope to get back at a later date with that. Should also say one thing, that the idea on the demo was to have an SPI connection here. Right now, we have stability issues, and we didn't want to bring that in a live demo. So everything today actually happens through the JTAG, which means that if you wave your hand above the sensor, it looks like there is a big delay. 99.9% of that delay is related to the JTAG stuff. Sort of making excuses for demos is always bad, but this is what it is. And of course, what should really happen is we connect the connect the sensor directly to the SoC. Unfortunately, again, this is a RISC-V summit, so the main problem with that is that we still haven't got the software for the sensor compiled for RISC-V. And we need the assistance from Aconeer to do that, and it hasn't really happened yet. So I said there are two neural networks, which is true, and it's because we basically look at distance and phase, or velocity, as it would be if you translate it into some physical property of the radar separately. We do classification using two neural networks based on the matrices that come from the sensor. And the result is really just one of the three classifications. So in order to leave some time for you to come forward, look at the demo, talk to Sergio, the wish we have, the wish we are bringing here, is for you to collaborate with us. We think that we're good at doing exactly what I told you about. We need applications. We would need quantized CNN models. We can run them on the existing solution. We would like to talk to you about on-chip interconnects, because for next generation we like to change things there. And we like you to challenge us. And here on the floor is myself talking, Sergio demoing, Joachim waving, and also Lawrence waving beside Joachim. Yeah, the rest of the team is back in Sweden. So thanks for that, and please come forward and move your hand over this, and I'll look that it actually works. Thank you for listening.
Thank you. Any questions or applications or challenges right now? And no, we can start setting it up. There's one question. Thank you.
Hi. Yeah, I have a question here for this near memory solution. Actually, I wanted to know that there are now solutions, companies are working to have these kind of smart memories that are either the memory has some kind of processing or they are very near the CPU. Have you considered replacing the FPGA implementation with that?
I mean, again, the FPGA implementation is just sort of a proof of concept, and it's a part of the path from concept to the actual silicon. So we're demoing based on the FPGA. We do near memory computing because we believe in it. We believe that it's difficult to challenge the density of normal RAM, so to say. And it's interesting in memory computing but we think that this path is very viable, and we like to prove that with power numbers to you in a while.
One more question if you want. I don't see any hands. So thank you again.
Thank you.